Welcome to chapter 2. We get to dive into calculus right away at this point. Let's going to bring back a picture from our past. Let's start off with the slope of a secant line, but let's start off with drawing our function. So we're going to have our random function. Maybe we don't know the equation for it. A little curvy here and there. So we're going to call that f. And let's suppose we have a value of x. We'll call that a. And so you know if you have a value of x, if you go straight up to the function in this case, you can find that corresponding y value that's going to be labeled as f of a. And let's pick a distance a little ways away. I'll exaggerate it for this point. It's about h distance away. We're setting all these up, but let's just make sure that we know the distance from here to here is h. So that would be labeled as a plus h on the x-axis. And if we were to find the corresponding y value, travel on up to the function, look over to the y-axis, and you would have f of a plus h. So if we were to look at the line through these 2 points that we have just drawn, remember when it crosses the function in 2 places, that line is called a secant line. We'll see if we can do our best to draw a straight line there. So we have our secant. And basically knowing the equation for the function and the value of the function at a certain x value, we might be interested in figuring out how can we figure out the equation of the tangent line at that x value. So what I'd like to draw for you is the tangent line at that point. And then I'll have a much better representation in a few seconds or so. But that green line is the tangent line. At the point x equals a. And remember, tangent lines only cross through the function at one place. So a few sections ago, if you remember how we did this, we took approximations using the secant line. And we noticed as we were getting pretty close to our value in question. So as we're making this h distance smaller, in other words, getting this a plus h point to be a little closer to the point in question. As we were doing this, the slope of the secant was getting pretty close to the slope of the tangent in the neighborhood of that point. So a lot of times what we like to do is you like to kind of blow this up. And if you were to look closely around x equals a, the slope of the secant line and the slope of the tangent line appear to be equal. And we definitely have a nice Desmos application to help you. I threw that in the section, but I'm going to bring that up in one more case. But let's remember what we did. Let's see if we can go through this one more time. Remember, if you're actually labeling what is the slope of the secant line, sometimes people like to use what we have M for slope. And if we were really specific as what we were doing, I'd use a SEC as a subscript to remind myself it's the slope of the secant. And remember, slope is always equal to the change in y over the change in x. And if we were looking at this in the sense of our 2 points, our 2 y values, If we were to write this out, this would be f of a plus h minus f of a all over, again, differences of the x's, corresponding a plus h minus a. So if we were to simplify the denominator just a little bit, I'm going to rewrite the numerator. A plus h minus a, we ended up getting the h in the denominator. So we have ourselves a way to get the slope of the secant line. Now, if I can pull up, let me reshare. We're going to reshare kind of a value to help you out with this. Here's a nice little Desmos graph. I included that in your sections for you to click on the links. But the colors might be a little bit off from our drawing. Oh, I think we had reversed the green and the purple. But if we are looking at the tangent line in this picture, it is purple, and the secant line is green. And the idea is to get the 2 points as close as possible by decreasing the distance between the x values. And you can kind of notice what's happening. Let's one more time. So here we have a bigger x value difference between the two ordered pairs. But as the points decrease in distances, the h value decreases. You notice that the points end up being right on top of each other, and that secant line ends up being right on top of that tangent line. You can kind of play with this if you want to go through this. You can change the function in the f of x part or the line, the point that you're looking at the tangent at. So that's a really nice animation to try to demonstrate what we were trying to draw by hand. But I'm always a big fan of drawing everything by hand because it does try to break down the geometry to the analytics here. So let's go back, finish some of our notes. So I included the link in the notes. So if you were on a PDF, you can click on it and you can play with that. And then also in the Canvas, you'll see there's a couple of links for you to look at. We finally get to think about, and remember, the idea is as the points get closer, we end up with a tangent line. So if we're trying to bring a little bit of calculus in this, we have a formal definition of what a derivative is. So the derivative of a function f with respect to x is, and then we have the boxed. We'll kind of see our notation. I'll go back and talk about notation in a second, but a lot of times you can just say derivative of f. Some people shorthand, they call this value in English, they say f prime x. If you were going to say that out loud. And what we're trying to describe when we were trying to get the h to shrink, the distance between a and a plus h to shrink, our job was to get h to approach 0. So once the 2 points are on top of each other, the distance between a and a plus h are not, it doesn't exist anymore. It's 0 between those. And so once this happens, if you're taking the limit of this expression, you're actually ending up getting the slope of the tangent line. So I'll kind of relate this a little bit more to geometry. We actually have the slope of the tangent line. To the function f at the point in little order pairs, x, comma, f of x. And that's referred to, a lot of times people will use the words point of tangency. It's a little fancier way to say it. But we actually kind of are looking at when we're introducing what a derivative is, it's really nothing more than the slope of the tangent line to a function at the point. We actually have a geometric connection here. So if I were to maybe specify this formula right here kind of gives us a generic way to calculate the slope of a tangent line at any point. And if we want specifics, if we know who the actual point is, then we would use the function notation. And instead of using x in our expression, we'll plug in a everywhere we see x. And we actually have the slope of the tangent line at the value x equals a. And so remember, if we're looking at on the exam or quizzes, we want to pay attention to directions. This limit definition is really important for you to be able to demonstrate. So if you were asked to do so, please don't take any shortcuts, even though we're going to find some very, very nice shortcuts in a couple sections. We want to make sure that you're okay with your algebra on all of this. So we're going to look at example 1. And remember that f of x plus h minus f of x over h is nothing more than the difference quotient we've been playing with. But let's utilize all of this. Here we go. We have the directions are specifying for us to use the limit definition to find the equation of the tangent line to the curve f of x equals x squared at the point x equals 2. And so some of you, if you have the function, this one's not a, this is a nice parent graph. We actually have our parent graph of, it's a parabola. And if we, I think I have a Desmos application on this one. Let's see if I can pull that up really quick. I think I have one of my other links that might help this one. Of course, you can use your TI to inspect this as well if you, well, you might not have Desmos out. So let's see. I do have the function f of x equals x squared. Right now I have a secant line, but if I were looking at the point around, it's supposed to be x equals 2. So at x equals 2, the y value is 4. I can use the sliders on the left if I'm playing with Desmos. So I have something pretty close. And the idea is to look at the secant line, decrease that h value so that the secant line ends up being the tangent line, and we have a graphical representation of what we're trying to find. We're a little bit off according to the order of pairs, but we're pretty close. So again, we're looking for the equation of that tangent line. And now we know a lot of algebra and we could probably find it without calculus, but we want to use the calculus to help us so that when we get to more complicated functions, we wouldn't be able to use algebra, we'd have to resort to limit definitions. So kind of keep that in mind. So let's go back to our notes. And if we remember from algebra, equations of lines are always going to require two things. Number one, we're looking at the point that the line is passing through. So I could say the point on the line. And in our case, the point on the line should be the point of tangency. Now, they didn't specifically tell us exactly what are the coordinates of that point, but they did give us the x value of that point. So we have x equals 2. And even though they didn't give us the particular y value, we're supposed to infer from the function that we have. Remember, it's f of x equals x squared. So if we were going to find that particular y value, if we were to find f of 2, That's going to give us 2 square, which gives us the 4. So that's our point of tangency. Now also, you've probably been through this before. A lot of times, every time someone asks you for an equation of the line, you end up using this slope-intercept form, y equals mx plus b. We are going to be interested in looking for the slope. That's usually pretty key. So in our case, if we're going to try to find the slope, we want to look for the slope of the tangent line. Now we just introduced how to figure this out. We go back, I can scroll back to my notes, and we actually have a formula to help us out. The slope of the tangent line to f at x equals a is, we can say f prime a, and that's the limit of the difference quotient, or the limit of the slope of the secant line. So if I want to kind of use that formula to help me, pretty soon you might not need it, but we could write it out if you'd like. Generics, f prime a equals the limit as h approaches 0 of f of a plus h minus f of a all over h. Sometimes you write it more out, you get a little more comfortable with using it. But in our case, our a is equal to 2. So what I like to do is just go and replace it, and I can use an eraser to do this, or we can just say, what is f? The derivative, f prime 2, derivative evaluated at 2. We can call up the limit as h approaches 0. Now plugging in f of 2, I'll color code this just a little bit, 2 plus h minus f of 2, again, all over h. Now at this point, it's a matter of simplifying the argument of the limit. So we want to kind of come up with an expression that applies to our function a bit. So what I'd like to do, if we're kind of playing with this, we actually already have f of 2 calculated. That was found by calculating the y value by plugging in x equals 2. So we could actually write that in right away. Now remember, I haven't calculated the limit yet, so I still have to keep writing the limit out. So I do have f of 2, that's going to be equal to 4. I'll color code that a little bit for you all. There's a minus sign that's subtracting that off. The next step, or stage, is to figure out what f of 2 plus h is. So that would be where, see, I'll use orange, help us out a little bit. We would have to take that function notation, we plug it back into the function. If you want to find the components, f of 2 plus h, knowing that f of x equals x squared, would be 2 plus h squared. And if you don't have the shortcut for expanding the binomial, you can just kind of go with what a definition of what it means to be squared. Repeating the 2 plus h times the 2 plus h. A little bit of math, we have 4 plus 4h plus h squared. And a lot of times people like to write the h squared first, the 4h second, and the 4 at the end, so descending order for you. But that's what we're going to replace in our function. So h squared plus 4h plus 4. And again, we're still all over h. Now, if you need a little bit more practice on that, take your time to understand where you're getting this f of 2 plus h. It's very important that you take your time and you're accurate with this. Otherwise, the limits end up being off. It gets quite frustrating, especially if you're in WebAssign. So again, we still have not calculated the limit. I'm still looking at it as h approaches 0. before I want to try to calculate the limit, I want to see if there's anything I can do to simplify this argument here. So to me, it looks like I'm able to neutralize the 4 and the minus 4. So I can look at this as h squared plus 4h over h. And notice we can't quite plug in h equals 0, no direct substitution yet, because h equals 0 makes the denominator 0, which makes the function undefined. So this is where we start using some of our algebra tricks to see if we can manipulate the argument before we start trying to plug anything in. And the idea is to see if we can get h to divide out from the denominator. And this one is a good candidate, looks like factoring. We're going to take the GCF out this time. So this is taking out a common factor of h. We'd be left over with h plus 4. Still all over h. And now this allows us to divide out the h's. You're only allowed to divide out factors, not terms. So you got to be really careful. And so we have limit as h approaches 0 of h plus 4. Now if you notice, if you were to plug in 0, you're not making the function undefined. So you finally have, by direct substitution, your slope of the tangent line is going to be equal to 0 plus 4, or you just want to say 4. I know you could do that in your head. So that's kind of key here. And then remember, this is the slope of the tangent line, just so that we are clear. We have the limit involved in that definition. Pretty much you start to assume what you're finding, but sometimes I label that with a subscript with a TAN to help me so I don't get too confused. Now, sometimes we get so excited after we've done all this work, we circle our answer, and then we might get it wrong because I believe the problem actually asks us for the equation of the tangent line. So don't get too excited. Always when you think you're done, reread everything. Let's go finish this off and look at the equation. If I was using point slope forms, and my favorite ways to go, remember I need to know the point that the line passes through, and that is the point of tangency, that's 2, 4. I'll write that down just in case. So we should have y minus 4 equals 4 times x minus 2 as the point slope form equation of the line. Sometimes, depending on the version of the answer, a lot of people like slope-intercept form. So we would just take this and solve it for y to get that. So let's distribute that 4 in. If we were to add 4 to both sides, we actually should get y equals 4x minus 4. And that is the answer to example 1. Pause for a second. So remember, if you're trying to find the slope of the tangent line, it really has to do with the limit definition. You're taking the limit of the slope of the secant. I kind of am going to re-look at this example in a slightly different way. This work that we've done at this point, it's great as long as the point of tangency is 2, 4. But the minute they change the point that they're interested in, we have to redo this process a lot of times. So most of the time, if I were to do a problem like this, I kind of like the generic version of the definition. So a little note here, I want to show you the way to get it. And we'll probably be using this a little bit more unless the function is super complicated. Because sometimes they want us to calculate more than one tangent line for every specific points. So most of the time, we might want to look at the generic expression. I guess I call it generic because it's not speaking about any specific point, just every x value. And that generic expression for slope of the tangent line, well, it's not quite slope yet, so I'm going to call it the derivative. Only becomes the slope when I know what the point is. So you can kind of see it's the same situation, except we're not using numbers for x. We have f of x plus h minus f of x all over h. And if our function in question is f of x equals x squared, I'll kind of write this off to the side. That was from the problem. Then we would take our expressions and substitute in function notation. So f of x is x squared. We would still need to calculate the component of the f of x plus h. I'll leave that up to you. I know we played with it a little bit, but f of x plus h at this moment is x plus h squared. And then we're still all over h. So let's take the limit as h approaches 0. If I were to expand out that binomial that's being squared, I have x squared plus 2xh plus h squared, and subtract off the x squared. And notice that if we're expanding, you can do the same idea as what we did above by rewriting the binomial twice and distributing or using FOIL to help you out. Or if you have a shortcut, that works well. So here on out, what we're looking at, see if you can simplify anything in the numerator, little combining like terms going on. It looks like I can subtract off the x squares, they neutralize. So we should get 2xh plus h squared over h. Remember, the reason why we're avoiding plugging in h equals 0 right now is because if you were to try to plug it in, you get that denominator of 0, making the function undefined. So it doesn't quite work yet until we can find a way to divide out that h. So to me, I am seeing it right now. I can pull out a common factor of h from the numerator. This is going to leave us with 2x plus h inside, and we still have h in the denominator. Just remembering that this h is a factor now, it can now be divided out. So we have our limit as h approaches 0 of 2x plus h, and finally you can plug in h equals 0 because it no longer makes the function undefined. So we're actually getting a generic formula for the slope of our tangent line. So at this point, if you were to look at it, you can quickly find the slope no matter what the point of tangency is. So that's really, really a big deal. Now if I change the point of tangency to at x equals 3 or x equals 50, once we have this nice generic formula, we'll find that slope right away. And I like to just, emphasize if you were looking at our current example, if we were looking at f prime of 2, that would be plugging in 2 times 2 to give us the 4. It is the same thing. See if I can point this over. It's the same thing as what we got here. So it's kind of like you're spending a little bit more time up at the front dealing with a lot of the algebraic expressions. And sometimes this is preferable because sometimes these algebraic expressions end up getting large numbers and we don't really have a need to find them if we know that we're just going to plug in values later. So I kind of prefer it that way, and maybe you might. We'll see. So I'll give you an alternative definition as well. I'll be honest, this one is okay. It's not my favorite. I find the other one a little bit more broad, but this one just works about the same. All it's telling us is we're not looking at maybe making the h distance go away. Instead, we're trying to make the points on the x-axis approach each other. So let me draw it out. It's pretty much the same thing that is happening, but people like to look at it slightly differently, but we'll go with it. So just in case you like it, and I'm totally okay with that, as long as we can show our work, we're in good shape. I'm going to draw out my function one more time. And we can go again, instead of using this x plus h business, we could talk about what's happening at A, and then what's happening at a point somewhere down the line to the right of A. And so if you look at the corresponding values, the corresponding y value at x equals A, we also have the corresponding y value at x equals x1, or x1 value. If we were to look at the slope of the secant line, or just the secant line in general, by connecting these 2 points, drawing the line as straight as we can. I'm a little bit off, but be generous. I have a crayon in my hand. So I have the slope of the secant line. If we were going to use a formula for that, the differences of the y's, f of x1 minus f of A, all over the differences of the corresponding x values. So just kind of remember, if you were thinking about slope in general, just so that we can all see, I'll draw kind of a mini slope triangle. We always talk about rise over run. But this mini slope triangle gives us the change in the y's. Remember, that's the 2 differences of the y's. Let me fix that a little bit. And then the horizontal distance is the change in the x's. So that's the x1 minus A, or you might know it from the previous definition as h. But they're using delta x to help us out. So the idea is, instead of decreasing the distance, you technically are, but they're saying what happens when we move this point closer to A? Well, on the line, these 2 points are going to move closer, just as they did with our Desmos, and they move closer and closer and closer until we actually get our slope of the tangent line. So you can kind of see, play with it on Desmos. It's the same situation that's actually happening. And let me label this as just the tangent line. And let me make sure that you're clear that this new formula is nothing really new. It's just another way to think about the points, but it is giving you the slope of the tangent line. So if you are interested, which I guess you're my captivated audience, we can use the above definition to figure out the same problem we just did in example 1. So I'll write it out and we'll kind of discuss it and we'll go from there. But you're probably guessing, well, we already figured it out. We already know the answer. And yeah, that's somehow another technique to help you see if you're actually on the right track. Sometimes if you know one technique, you can use that to help you out with the other technique. So here I am using my formula. So instead of approaching a random value of x, we actually have the x value of 2. So we're using function notation to plug that into our expression. So I should have f of 2. And then I still have x1 minus 2 as well. So remember, the way it's working is that these second values are getting plugged in. Well, you don't have to call x1 x1. It is an x value. It doesn't matter what we're looking at. So they kind of take the idea, and instead of looking at x1, it's still function notation. So for example, if I can go off to the side, we know f of x equals x squared. Well, instead of using x, you can plug in x1, kind of like what we were doing with some delta epsilon discoveries earlier. And we kind of wave our hands a little bit because x squared is the same as x1 squared. It's the same idea. It just depends on wherever you're looking at. So what they do is they take this, they wave their hands a little bit, and they say, hey, that's the same thing. Is the limit as x approaches 2. So all they did was re-look at the notation. If you're going to speak about x values, you can call x x1. You can call it x2 if you wanted. But we just kind of use this to simplify our notations and our understandings just a little bit. So let me just rewrite it so that you kind of see what I'm looking at. So we have f of x minus f of 2 all over x minus 2. And then this is what is kind of helping us with the notation. It helps us to see what to plug into our expression, our argument for the limit. You'll notice that we had the f of x was x squared. So we can plug that in right away. And actually we know f of 2, which gives us 2 squared is 4. Still in the denominator, we have x minus 2. So some people like the definition because in some cases it does make the numerator a little bit prettier. We notice that this is not so much of a complicated factorization. It's another difference of squares. One more time, I'll point out, I would not be able to plug in x equals 2 directly at this time because you would be saying the denominator 2 minus 2 being 0, and that's where we run into issues. But we utilize some of our factoring techniques to see if that allows us to eventually use the direct substitution. So I just broke up that difference of squares into its factorization. And we're getting lucky here. The x minus 2's divide out. So I still have the limit as x approaches 2 of x plus 2. Remember, I couldn't quite finish off until I plug this back in, and that's where we're using the substitution. Now we can do this because we do not have an undefined function. So now take this, compare it to example 1, and you'll notice, hey, it's the same. So we're happy with either way. I guess I just go with example 1. Maybe it's like the first way you learn something, it just sticks in your mind or something. But feel free, if you really like this one and you see that it becomes nicer with some of the algebra, I'm happy to entertain that too. So let's make this a little more exciting. We've been dealing with parabolas. The next thing I want to play with is, what if we have a more complicated function? Got ourselves a rational function here. So example 3, it's asking us to use the limit definition. So I have to emphasize that. And sometimes right away, if that's what they're asking from me, sometimes I'll write it out to remind myself before I get too into all of the computations. That gives me a chance where I don't miss anything. Okay, so I'll write out the generics. We have f of x plus h minus f of x all over h. So that reminds me, this is what I have to use instead of any other technique I might be learning. So remember, when we try to calculate this, if you were going to plug in h equals 0 right now, it's not going to work. It makes everything undefined. So we're going to do this in parts. We want to look at the f of x plus h. Sometimes what I'll do is remind myself, and maybe I'll do this in colors. F of x is already defined for us. It's 1 over x minus 3. If I were to plug in f of x plus h, I'm replacing x, so that's going to be x plus h minus 3. So x plus h minus 3. Those x plus h's can't be split up. So now what I'd like to do, I'm going to take a little time and substitute this into our part. And maybe I'll leave a little more space because it looks like I'm getting complex fractions. I don't always feel that's enough space. So here's my big denominator, my fraction bar. F of x plus h is 1 over x plus h minus 3. We would be subtracting off f of x, 1 over x minus 3, and we're still all over h. So now we run into a little idea where this is not like the standard ones we've been doing. If we have lines or polynomials, a lot of times like things would cancel out right away. We wouldn't have to think much. We just have to worry about factoring. But what I might say, whenever you run into stuff that has complex fractions, usually the way to go is to see if you can simplify that complex fraction a bit. So maybe my focus is looking at this numerator and perhaps combining over a common denominator would help our cause. So let's take a little time on that. Eventually, this is all about patience. So I want to kind of keep in mind, I'm looking at trying to find maybe a least common denominator. My goal would be to rewrite that numerator as a single fraction, combining over the common denominator. When I inspect what's actually going on, looks like I have two separate denominators, so I kind of feel like there's nothing I can do. They don't really factor, but I do know the LCD would be the product of those two. So if that is the case, I would then try to figure out what each one needed in order to turn into the LCD. And the answer to that is just, what does it not have? So I know that the first part needs an x minus 3 over x minus 3. So I would have 1 times x minus 3. I would still have this minus sign from the original subtraction. The second part needs x plus h minus 3 in the denominator. So that's why we're multiplying the numerator by the same thing, a little fraction math here. So now what we're looking at is subtracting off x plus h minus 3. But a little caution to you is when you are looking at subtracting off more than one term, we have to remember that we need to make sure we're distributing the -1. So be careful there so that, if you mess up in one place, sometimes it doesn't end up being right. But that's kind of the #1 mistake a lot of us make. So let's make this a little prettier. I'm looking at the denominator. I have x plus h minus 3, x minus 3. And now I'm just going to simplify what that numerator is. We have x minus 3 minus x minus h plus a 3. And this is looking promising, I see. Looking at that numerator, I can tell that I can cancel out some of these terms. X minus x, -3 plus 3. And now we're getting to be in good shape. I have the limit as h approaches 0. I would have got to be a little careful when we're going through these complex fractions. Let me see if I can write this a little straighter. I now have a denominator x plus h minus 3, x minus 3. And then the numerator of that fraction was negative h. And the denominator is h of our entire complex fraction. Now what I'm looking at, there's more than a way to approach it. You could go in the root if you needed to, and I'm going to leave some space onto the right side, but we could take the case that, hey, whenever you divide two complex fractions, you can rewrite division. So we can see this, numerator divided by denominator, but anytime you divide two fractions, you're actually multiplying by the reciprocal. So you can play with it that way if you'd like. But I kind of see a little shortcut. And the fact that if I am looking at this complex fraction and it's only got one term in the denominator, I could actually rewrite it a little bit more pleasing to my eyes. So a little fancy math trick, nothing too crazy. But if I'm looking at this h right here, you're dividing by h. And so just kind of a little bit of a side note, whenever you're dividing by h, you're technically multiplying by its reciprocal. So in the same manner, I'm going to take my h, instead of writing it as divided by h, I'm going to write it as multiplying by 1 over h. So I'm taking that and multiplying it by the entire fraction. So then you see, we no longer have a complex fraction. Interesting. We get a little fancy when we're in calculus. Feel free, do it how you decide. Whatever works for you is always best. So now I'll notice that I can divide out the h's, and I should get a negative 1 on top when you divide everyone out. I have x plus h minus 3 times x minus 3. You need a little bit more space here. But sometimes you're kind of looking at it, you're like, wait, I thought we're supposed to get rid of all the h's in the denominator. Well, be careful. We only have one h in the denominator, and if that is 0, if that goes to 0, sometimes that's how we write that, we don't have an issue. We actually don't need, to have anything to lure us away from using the direct substitution. And actually, if I already know that's going to 0, what do I get at the end? That's actually me substituting in for h. I have negative 1 over x minus 3 and times x minus 3, which, if I can, I'm going to move a little bit off to the side of this example. We'll deal with that later. That's negative 1 over x minus 3 squared. So we just calculated the derivative of 1 over x minus 3 using the limit definition. And I just want to emphasize, there's a lot of algebra coming back from our past. It does give us a chance to flex those muscles a little bit. But always start off with the basics. What do you know about replacing each component? F of x plus h, f of x, and then use what you see to kind of motivate what you're supposed to do later. So a lot of the math from our past comes back. And I know you probably heard me talk about like f prime x. I'll kind of give you a way that we talk about derivatives so we don't have to keep writing out derivative every single time. So there's a few different ways to play with the derivative, and I'll kind of give you a few of them. A lot of times you see this notation first. We have f prime x. If I'm not mistaken, this might have been Newton's way to do this, using f prime x, or sometimes if we know that y is equal to f of x, it's also equal, it's the same thing as saying y prime. So maybe we see this way. So if you want to say this in English, and let me make that a little prettier. It bothers me a little bit. Here we go, f prime x. So that's the first derivative, or just the derivative of y. If you want to say this in English, sometimes people say f prime. We already wrote that out. Or this one, we say what, y prime? Shorthand. But we're still referring back to the derivative. Now, another way, remember, calculus was invented by two separate people on different parts of the world. We have someone named Leibniz, and this is another notation that could stand for the same thing. So if I can write this out, we can talk about this as dy over dx. And just in case you're wondering, that's where I had my notation. See if I can write this out, spell it correctly. This guy doesn't always get as much credit. I believe Newton's more popular. But Leibniz used this notation. And we're going to explain what these mean in a second. But this notation is really useful in our application problems. So really useful. Sometimes you guys get a little annoyed with writing stuff out, but it actually gives us a hint of what we're doing later. So we see some application problems. I'll throw some in for this section and kind of relate this to you, but 2.8 is probably where you'll utilize this a lot more. Another way you might see derivative notation is kind of using it as an operator. So let's kind of finish this one out. You could see that in a way, they split this up. So the derivative of the function in each cases. And using this as an operator, it's more useful maybe in later classes. Kind of like using the derivative as an operator, like what you would do to both sides. So we may see that a little bit later, but more so in the next maybe Calc 2 a bit more. And so if I could kind of give you kind of notation, whenever you are calculating the derivative, let's look at this notation one more time. The language, the derivative of y with respect to x. Notice how in the Leibniz notation, we have dy with respect to x. So the with respect to part is on the denominator. We also say the same thing when we're using the f prime x and y prime. It's more formal to use derivative of y with respect to x. Most of the time we're taking derivatives of y with respect to x if you are strictly dealing with coordinates x, y notation. But remember, life is not all in x and y's. They could be in different variables, so it does matter with what variable you are taking the derivative with respect to. So be careful. And I don't want to get you too excited, but in Calc 3, sometimes you're taking derivatives with respect to different variables at different times. So just knowing what you're doing here is going to help you greatly. So if I were to speak about these, maybe off to the side, just so you can see. Remember we were talking about was it f of x? I'll show you this little notation of what we were doing. So like from example 2, is this example 2? No, it's example 3, excuse me. We started off with f of x equals 1 over x minus 3. Well, if you're going to denote the derivative when it's given to you as an f of x, a lot of you might say f prime x. And that's where we got our -1 over x minus 3 squared. Sometimes maybe they gave you the function where it was equal to y instead of f of x. So this might be a case where you either use the Liveness notation as you are calculating the derivative, or you might use the y prime. Same thing. So moral of the story, kind of depends on how you start. If you started with an f of x, you might as well use f prime x, unless there's a reason to, maybe there's an application, then you would go straight to using the dy dx, so we say. So notation, it's fun, but it's only fun if you understand it. So take some time to review that. Speaking of applications, such a good segue. We're going to look at, let's define this, this Liveness notation. We'll look at dy dx. And I'm looking at this, a lot of times you guys look at the fact that, it does look like a fraction. And there are cases against where they don't like you to think about it as a fraction. Sometimes we do, sometimes we don't. That's all I'll say for now, but I'll let your next teacher deal with that part. But I would like to kind of explain how it applies to what we're dealing with in some of these applications that we're going with. When you see this notation or any sort of derivative, it's actually a rate of change. Well, slope is a rate of change, but we're clear that it's a rate. And it's representing the change in the value of y per unit change in x. So that's where we're getting the fraction from, the word per, little fraction bar right there. Now, this is nothing different than what you've been dealing with slope. For example, if you had this notation, y equals 3/2 x minus 4, when you talk about the change in y over change in x, they're saying for every 3 units in y, we have changed 2 units in x. If we change this to unit notation, what do we have, 1.5? For every 1 unit of change in x, the y changes by 1.5 units. So we've applied this before, really rate of change, we speak about it as the slope. But they really want you to look into this a little bit more in depth because we're going to use derivative notation to help us out with some of these. So I'm going to play with kind of introducing you to maybe cost and see how it looks when we are, maybe we're not in y's and x's, we're now in c's and x's. And so if we're kind of looking at the difference between these two statements, there's function notation and there's something with a derivative. Let's kind of interpret. So we don't really have anything to calculate this time, but we want to see what we can do to understand this. So a little bit of function notation that we know and love. This one would be, if we were trying to say C of 10 equals 480, we first have to understand what units everyone is defined in. So the X stands for number of military drones, and then the C stands for the cost, but it's in thousands of dollars. So we have to be careful. Sometimes they throw that in. So if I was to write this out, I mean, I can say, hey, when X equals 10, C equals 480. That is true, little function notation. But if I'm going to interpret this in English, I can say, okay, the cost of making 10 drones it's not just 480, it's 480,000. So we're going to be really careful by including the appropriate units. That would be a big mistake if your company accidentally only charged $480 for the 10 drones. Someone would get fired. So kind of be careful on that. So that's kind of some function notation that we know and love. This one's a little bit more in depth. We do kind of use the rate of change to help us. A lot of times when I'm dealing with derivative notation, when they use primes, I'd like to kind of give you a hint and maybe use the Liveness notation. And so if I'm looking at this, if we go back to our past and we saw f prime x, f prime x is the derivative of y with respect to x. So I'm kind of looking at it in this stage, not quite with numbers yet, but I would like to rewrite it for myself as the Leibniz notation. And I have to figure out what you're taking the derivative with respect to. And apparently the way this is looking, it looks like it's taken with respect to x. So that's what's happening in the denominator of the said notation. And that must mean we're taking the derivative of cost with respect to x. And then what I'd like to do is just figure out the units to each of these values. So I'm not really doing sentences yet, but I could kind of ask myself, okay, what is C in terms of? Cost is in terms of dollars in thousands. And then X is in terms in number of drones. So if I'm looking at this dy dx application definition, the change, rate of change representing the change in the numerator value, that's cost, per unit. And so per unit, unit is singular. This would be referred to as one drone. That's our X value. So I'm just trying to figure out who the units are. So that actually is going to help me a little bit. And so if I can kind of give you I'll give you some ways to think about it, and then we kind of explore this a little bit more. We spoke a little bit about, instantaneous rate of change, average rate of change. We're going to figure this out, that slopes of tangents, we have some instantaneous rate of change. So if I'm going to write this out, if I look at this notation, when x has reached that level, at that moment in time, the function's going to change at that rate. So it might be something to kind of write down. So as x has reached this level at that moment in time, so this is where instantaneous comes into play, but I'm just going to leave it. We'll inspect it more. At that moment in time, the function will change at the rate. just kind of a generic idea of what's happening. Now, if I'm going to apply this to our actual concrete examples, we're talking about cost in thousands of dollars of drones, ex-military drones. We're looking, so if I can finally talk about it this way. So when they say has reached this level, we can say as the number of drones increases, and we'll get into this later. I'll give you this definition to kind of sit in your mind, and then I'll give you an alternative one. But this is nice to plant the seed in your mind. As the number of drones increases from 10 to 11, so we're noticing unit changes. So X values change by ones, so 10 would have to change to 11. The cost will increase the Y value in this case, or the value of the derivative. So it will increase 11.25, but if we want to be careful, it's thousands of dollars. So what does that mean? By the way, you know, $11.25 thousand, play with it, 11,250. So we could say, just kind of, I'll simplify it a little bit more. So remember, one more time, we're always talking about per unit change in X. So when you look at your X value, you're thinking, how is it changing from what it is now to one more unit beyond? So that's where we're getting the 10 to 11. Then the given rate will be whatever this calculation is. Just be careful with the units. So one might be able to say the cost of the 11th drone. There's two thes in there. Cost of the 11th drone is going to be 11,250 according to the constraints. So just kind of look into that. Sometimes it's not obvious right away, but remember, we're always talking about per unit change in whatever the X is or whatever we're referring to in the, I'll say the denominator of that Liveness notation. We call it denominator. I know it's not really, but it works out that way. We'll leave it at that. And if you want to think about this alternatively, I could probably say, you know, when 10 drones have been made, the cost of production is increasing at a rate of $11,250 per drone. That might be a little bit more useful. So maybe we can look at this. Alternative statement. So another way to think about this, and let's write this out again, the derivative. So if I can think about it this way, little derivative notation. We ended up getting it's 11,250 for one drone. So when 10 drones, I've already said it, but it's not bad to write it down one more time just in case we miss it. When 10 drones have been made, the cost of production is increasing. Why would we say increasing? Well, let's double check. What was the sign of that? Yes, the sign is a plus. Well, it's not written, but it's implied. So the cost of production is increasing at a rate of $11,250 per drone. there's that fraction notation. Fraction bars usually mean per. That comes back. So we'll revisit this again. And actually, we'll do this in the sense of maybe velocity and position in the next example. But you will see this type of interpretation happen again, and it will apply a little bit more to us calculating values. So we'll get there. So one last example for the section. We're going to look at this notation in terms of another popular application in calculus, velocity. I think we have velocity and, yeah, movement. So we've got ourselves S of t. So instead of x and y, sometimes this is really helpful for myself in calculus. I know when I see function notation, x and y usually kind of go along with this. So if I'm looking at S of t, then it appears like my ordered pair, the way I'm looking at it is that it looks like the independent variable is time, and then the position is the dependent variable. So that could help me a little bit in my interpretation. So S of t is the position function of a particle moving along a straight path. And right now we're going to keep in calculus 1 straight path, but you know that's not how the world works. So we live in 3D. Particles can move in all directions. So we'll kind of develop that more if you go to calculus 3. The particle is allowed to move in any direction, but right now we're going to keep it nice. So we're moving in a straight path. S is measured in meters and t is measured in seconds. We define motion to the right to be positive and motion to the left to be negative. Let's interpret the following. So we look at part A, and then I'm looking at this and I'm noticing there's no derivatives involved. It's giving me maybe function notation. So that's kind of where I'm looking at my ordered pairs to help me understand. If I want to, I can rewrite onto the side. T is equal to 3, S is equal to 8, according to this notation. And if it helps you, you can write the units. T is in seconds, S is in meters. So we might say after 3 seconds, or, well, I'll write something there because a little bit of physics might come in. But after 3 seconds, the particle is 8 meters to the right. And why to the right? Let's go back. What was the value on the S? Was it positive or negative? Positive. So 8 meters to the right of its initial position. Just kind of look at where you're located. Now remember, we're moving along one direction. I'll leave it as this, it kind of helps. I know we're not really talking about Y values, but we'll leave it there. So just be really careful here too, if we're being really specific. When I say this in this statement, physicists might be a little bit mad at me. Technically what this means, oops, let me write this down. It really means at 3 seconds. But a lot of times when we say after 3 seconds, it's more of a common way to say it. So I should kind of be a little bit more detailed, but it's just what's happening at 3 seconds right away. Okay, so a little bit more, almost there. Now we're running into an expression that has derivative in it. So again, this is the Liveness notation. So again, what I always want to recommend, my little hint to myself, is let's rewrite it so we can see where the units are located. So according to this notation, it looks like we're taking the derivative with respect to t, with respect to time. So that's why we have the denominator. And it looks like that would be the other variable, derivative of s, derivative of position with respect to time. And then if you can, go through and say, well, what's the units on s? We have ourselves meters. And the units on t is time. We have ourselves seconds. And my friends, you know, meters per second. Meters per second, that sounds familiar. Sounds like we have some sort of velocity going on. Just trying to make sure the pen's working again. Guess not. Might be time to go. It is almost time to go. So this, by the way, is velocity, meters per second. That's how we measure that. So this is the final case of kind of understanding, oh yeah, meters per second, that's a rate. We're comparing two different units to each other, meters versus seconds. So they're not both the same type of unit, one's distance and one's time. So if I'm going to interpret this, I'll say this, same notation. So after 5 seconds, or we should say right at 5 seconds. So after 5 seconds, the particle is moving to the left. Again, why did I say left? Let's go back. We see that negative sign. At a rate of, now what's the calculation? 2 meters per second. Or some people like to write it as 2 meters over seconds. We've seen that before too. And so this is the case, again, the note, derivative, and rate kind of go hand in hand. So maybe write that off to the side. Anything to help to keep this clear. So a little bit of theory here. So derivative and rate. Usually that's what we hear about when we mention derivative in applications. So if we want to tie this all up, just so that when we see these again, we will be dealing with these in terms of calculations. If we have ourselves the position function and we take the derivative of the position function, we are going to get ourselves the velocity function. A lot of times we label that as v of t. And the velocity is a function that is a vector. I know we haven't dealt with vectors in a while, maybe never, from trig class. Remember, vectors have magnitude and direction. So we have to be careful because magnitude is how long it is, direction is whether you're moving to the left, to the right, up, down, etc. And I know a lot of times we get confused with velocity versus speed, but just in case you're wondering, speed, sometimes people call that rate, and that kind of confuses everyone. But speed is the magnitude of velocity. Let's spell magnitude right. There we go. Magnitude. So when you're talking about magnitudes, we're never negative. So if you said you went 60 miles per hour, you're never decreasing. You are constantly 60 miles per hour. That's a positive speed. Later on, if when the time comes, maybe at the end of this section, if you had wanted to take the derivative of the velocity function, you can do it for the heck of it, but it actually has an application involved with it. It actually is the acceleration function. So a lot of times there's a lot of connections between position, velocity, acceleration, as well as speed. So we're going to revisit that a little later with more computations, but this should get you situated for section 2.1. We'll see you in 2.2.